In this video, we're going to use trapezoidal and midpoint rules to approximate an integral, and then use the area formulas to figure out about what the error is in the approximation, or at least an upper bound for the error in the approximation. So let's look at the integral from 1 to 2 of e to the 1 over x dx. We're being asked to find an approximation for the integral using 10 subintervals for each of the trapezoidal and midpoint rules. So again, first we'll calculate our delta x, which will get 0.1. For the trapezoidal rule, the multiplier out in front is delta x over 2. The endpoints of our subintervals are going to be 1, 1.1, 1.2, all the way up to 2. Plug those into our function, our integrand, and remember the ones that aren't the endpoints, so 1.1, 1.2 up to 1.9, we'll multiply by the coefficients of 2. Use our calculator and get approximately 2.022 as our estimate for our integral using the trapezoidal rule. Now with midpoint rule, we need to plug in the midpoints of each of our subintervals. So the midpoint in the interval from 1 to 1.1 is 1.05. From 1.1 to 1.2, it's 1.15, and so on up until we get to 1.95 for our midpoint. The multiplier out in front will be just delta x, so that's where the 0.1 comes from. Using our calculator again to simplify the sum, we'll get approximately 2.019 for the approximation for the integral. Using the error formulas for the trapezoidal and midpoint rules, or the upper bounds for the errors on the trapezoidal and midpoint rules, we need to calculate how big the second derivative can be on the interval that we are looking at. So the first thing we'll do is we'll take the second derivative, and that's what this computation is here. We have to use the chain rule for the first derivative, use a quotient rule for the second derivative, and simplify. You should get 2x plus 1 times e to the 1 over x to the fourth. We want to know how big this thing can possibly get on the interval. Turns out that the biggest that this can get is at the left-hand endpoint of the interval. So the second derivative is decreasing in this case over the interval. And if we plug in 1 into the second derivative, we'll get 3e. So the largest that the second derivative can get is 3e. The trapezoidal and midpoint rule bounds for their errors look very, very similar. The only thing that's different is that we divide by 12 for trapezoidal rule. We divide by 24 for midpoint rule. So we do 3e, that's the maximum, multiply by the cube of the length of the interval. In this case, that's just 1. And then divide by 12 times the number of subintervals squared for trapezoidal rule. For midpoint rule, you divide by 24 times the number of subintervals squared. So we see that the error in the trapezoidal rule in absolute value is at most about 0.007-ish. For the midpoint rule, it's about 0.003-ish. If we're looking to bound the error by a specific value, we use the same formulas. We just need to figure out how large n needs to be in order to be able to do that. So for part C, we're asked to try to bound the error to within 0.0001. So again, we set the error formula for the trapezoidal rule less than or equal to that particular value, because if that upper bound is less than 0.0001, so is the error. If we rearrange this equation to solve for n, we get n needs to be bigger than or equal to something a little more than 82. Well, certainly n needs to be an integer, and we need to be at least that much, so we're going to use 83 subintervals for trapezoidal rule. Do a similar computation for midpoint rule, and you'll get that n needs to be at least 59 subintervals to get it to within 0.001.